What could happen to a planet if its only natural satellite suddenly vanished from celestial mechanics? At first, this question sounds like pure fantasy, almost like a thought experiment whispered late at night. And yet, even hypothetical modeling of such a scenario helps us better understand how fragile the Earth system truly is. The stability of our planet is not a given. It is built from a delicate balance of gravitational forces, rotational motion, and continuous energy exchange. And the Moon is one of the key elements of this balance. Its influence quietly shapes the world around us. It moves the oceans through tides. It slowly alters the rotation of the planet. It stabilizes the tilt of Earth's axis. It regulates climate patterns. And it even reaches into the biological rhythms of living organisms. Because of this, any mental model in which the Moon disappears is not merely a theoretical or psychological exercise. It is an attempt to describe the deep fundamental mechanisms that make Earth a habitable world. Let us imagine a very specific situation. The Moon does not collide with Earth. There is no impact, no explosion, no orbital catastrophe. It simply ceases to exist, quietly, instantly. An object whose mass is roughly 1/80th of Earth's mass disappears. A mass that has continuously influenced our planet for more than 4.5 billion years. Approximately 7.4 times 10 kilograms of matter are suddenly removed from the system. Despite its relatively small size, the Moon produces effects vastly disproportionate to its mass. The absence of that mass immediately alters the geometry of tidal forces. The amplitude of deformation within Earth's crust decreases. Ocean dynamics reorganize themselves, and the moment of inertia of the Earth-Moon system changes. All of these processes begin at once. They unfold simultaneously, forming a cascade of changes. That can be divided into several levels: immediate, short-term, long-term, and evolutionary. Immediate consequences. The first and most noticeable change occurs in the tides. The Moon is responsible for roughly 2/3 of all tidal forces on Earth. When this source disappears, the height of waves, the amplitude of tides, and the distribution of oceanic water masses are instantly altered. The tidal wave driven by lunar gravity vanishes. The planet remains under the influence of solar tides alone, which are approximately 2.5 times weaker. This means that many coastal regions, once accustomed to strong tidal movements, would now observe an almost motionless ocean surface. Water would still rise and fall, but far less noticeably. In some areas, the difference would be measured in mere tens of centimeters. Yet even this subtle change is enough to disrupt biological niches that evolved around cyclical fluctuations of sea level. A natural rhythm disappears, a rhythm that millions of marine organisms depended on. This loss would be one of the first consequences, though far from the most profound: rotation and time. Tidal deformation of Earth's crust would also disappear. These deformations are thousands of times weaker than those affecting the oceans, but their contribution has been crucial to the gradual slowing of Earth's rotation. The Earth slowly transfers a portion of its rotational energy to the Moon, and the Moon, in turn, slowly drifts away by just a few centimeters each year. If the Moon vanishes, this channel of rotational energy loss vanishes with it. Earth would no longer slow down at the rate it has for billions of years. Over long timescales, the length of the day would stop increasing, as it once did. Today, a day on Earth is significantly longer than it was in deep geological history, and this change is a direct consequence of Earth-Moon interaction. In a future without the Moon, the length of the day would eventually stabilize. Not instantly, but after the planet adapts to a new energetic equilibrium. The most critical change, axial tilt, the most profound consequence, however, would emerge from changes to Earth's axial tilt. The Moon acts as a stabilizer, holding Earth's axis at approximately 23.5 degrees. Without the Moon, This angle becomes far more sensitive to gravitational perturbations from other planets, especially Jupiter. Some models suggest that without lunar stabilization, Earth's axial tilt could vary from nearly zero to values approaching 40 degrees. Such fluctuations would trigger dramatic shifts in climate zones. Extreme cooling would alternate with intense warming. Ice caps would migrate across the planet, and solar energy would be redistributed across Earth's surface in unpredictable ways. The climate would become less stable, less predictable, and far more vulnerable to long, chaotic cycles of transformation. Impact on life. Life adapts to rhythms, to the lunar month, to tidal cycles, to the alternation of day and night, to seasonal changes in solar energy. Even the bright nights of a full moon affect animal behavior, reproductive cycles, and navigation strategies. The disappearance of such a powerful rhythmic source creates an entirely new evolutionary challenge. Species dependent on tides would be among the first at risk of extinction. Animals that rely on reflected moonlight would lose a crucial point of orientation. Over hundreds of thousands of years, the biosphere would adapt. But in the initial era, it would experience severe ecological stress. Geological consequences. Hypothetically, the disappearance of the moon could also affect plate tectonics. Tidal forces slightly deform the lithosphere, creating a weak but constant influence that enhances tectonic activity. Without this influence, volcanism might decrease, not dramatically, but noticeably. Some models suggest that a young planet without a large satellite could experience periods of tectonic stagnation. For modern Earth, this effect would not be catastrophic, but its removal adds yet another layer to the planet's systemic reorganization. The reduction of gravitational flexing could also alter the frequency of certain types of earthquakes. The night without the moon, there is also a quieter change. The moon is the largest reflector of sunlight in near-Earth space. Without it, nighttime illumination would drop by nearly 20 times. The sky would become profoundly darker. On land, this could increase nighttime cooling and amplify temperature differences between day and night. On a global climate scale, the effect would be subtle. But at the ecosystem level, it could significantly alter animal behavior patterns. A planetary comparison. Scientists often explore similar dynamics. By studying Mars, Mars has 2 small moons, and its axial tilt varies far more freely. Models of Martian climate show cycles lasting tens of thousands of years, during which the planet oscillates between extreme cold and relative warmth. A similar fate could await Earth. Our planet has enough mass to remain generally stable, but it lacks the ability to automatically stabilize its axial tilt without the moon. Thus, the very idea of the moon's disappearance forces climate science to reconsider many foundational assumptions. Orbital resonance and deep time. The moon also influences Earth's orbital resonance. Our planet's orbit is intertwined with the rest of the solar system through a complex web of gravitational interactions. The loss of the moon redistributes mass within this system. Over immense spans of time, this leads to subtle changes in Earth's trajectory. These changes are far too small to dramatically alter Earth's orbit, but over millions of years, they can influence Milankovitch cycles, natural rhythms of climate change, driven by eccentricity, axial tilt, and precession. Without the moon, precession accelerates, tilt becomes less stable, and climate cycles grow more chaotic. The human dimension. And finally, there is one more aspect: human perception. For humanity, the moon has been the oldest calendar, a source of myth, a measure of time, and a symbol of stability in the night. Its disappearance would not only be a physical event, but a psychological shock. Human civilizations shaped their rhythms around the lunar cycle. And in a sky without the moon, something ancient inside us would quietly notice that the night is no longer the same. And even if modern society has largely lost its direct, practical dependence on the phases of the moon, the subconscious sense of its presence remains deeply woven into human culture. The moon is no longer required to measure time, to guide navigation, or to regulate daily labor, yet it still exists as a quiet psychological anchor. Its sudden loss would create a subtle but persistent feeling of instability, a feeling that is difficult to quantify, impossible to measure precisely, and yet impossible to ignore. And still, at the center of this entire model stands the main question: how quickly would Earth adapt to a new reality without the moon? The answer depends on the nature of the scenario itself. If the disappearance of the moon is treated as an instantaneous loss of mass, the system's response becomes sharp and abrupt. If instead, the model allows for a gradual weakening of lunar influence, some processes may be partially absorbed and adapted by the planet itself. But in every case, the disappearance of the moon would represent the largest experiment in the history of Earth's celestial mechanics. Under these conditions, the planet would continue to function, but it would function differently, with less predictable climate cycles, with weaker tectonic activity, with altered biological adaptation, and with a modified rhythm of planetary rotation. Climate stability and intelligent life. What determines the climatic stability of a planet on which intelligent life has emerged? This question becomes especially sharp when we remove from the system an element that, for billions of years, kept Earth's rotational axis within a relatively narrow range. The moon is not merely a celestial object reflecting sunlight. Its gravitational influence shapes one of the most critical parameters of Earth's climate: the stability of axial tilt. This tilt ensures a relatively gentle and balanced distribution of solar energy across the seasons. When the moon disappears, the mechanism limiting fluctuations of this tilt disappears as well. That is why a climate model constructed without lunar influence acquires traits of chaos. On geological timescales, this chaos reshapes the very nature of the planetary environment. Axial instability. Earth's axis is tilted by approximately 23.5 degrees. This value is not a perfect constant. It slowly oscillates under the gravitational influence of other planets in the solar system. The moon acts as a stabilizing factor, reducing the amplitude of these oscillations. Without it, the tilt becomes far more sensitive to external perturbations. The gravitational contribution of Jupiter, with its immense mass, begins to dominate. This creates periods during which the axial tilt may increase or decrease significantly. Some models show that this range of oscillation could extend from near zero to values close to 40 degrees. Such extremes imply dramatic reorganizations of climate zones. Atmospheric circulation shifts. Ocean currents reorganize. Biomes migrate across continents. The Earth, in this scenario, begins to resemble Mars. A Martian analogy: Mars lacks a large satellite capable of stabilizing its axis. As a result, its axial tilt changes freely, producing cycles of severe climate transformation. Martian history suggests that a planet without such stabilization can experience epochs of global cooling, when polar ice spreads nearly to the tropics, followed by warmer periods when ice retreats. Applied to Earth, this would mean eras when ice blankets large portions of the continents, alternating with periods of partial warming. The difference lies in scale. Earth is more massive. It has a denser atmosphere. It possesses vast oceans. These factors soften the extremes, but they do not eliminate them. Redistribution of sunlight, changes in axial tilt, redistribute solar energy. As the tilt increases, polar regions receive more sunlight in summer and far less in winter. Seasonal contrasts become extreme. Polar summers grow surprisingly warm. Glaciers melt rapidly, releasing enormous volumes of meltwater. Polar winters, however, plunge into deep cold, forming massive ice domes. In equatorial regions, the situation evolves differently. Greater axial tilt reduces seasonal variation, but strengthens the influence of global circulation systems, transporting heat and moisture. This causes deserts, forests, and savannas to shift over distances of thousands of kilometers. Such dynamics eliminate long-term climatic stability. Oceans and paradoxical cooling. Earth's climate is tightly coupled to ocean circulation. One of the most important systems is the Atlantic meridional overturning circulation, which transports heat from the equator toward northern latitudes. This circulation depends on water density, which itself depends on temperature and salinity. If the moon disappears and axial tilt begins to vary, polar ice melt cycles change as well. During periods of warm polar summers, vast quantities of fresh water enter the oceans. This fresh water lowers surface density, weakening the sinking of cold water and disrupting the global heat conveyor. As a result, northern regions may experience prolonged cooling despite increased summer sunlight. This appears paradoxical, but climate systems do not always respond linearly. Excessive ice melt can trigger cooling, where warming was expected. A fragmented climate over time. Earth's climate becomes fragmented. In some epochs, the equatorial belt becomes warm and humid, supporting intense biological productivity. In others, it dries out while polar ice expands. This restructuring disrupts many climate rhythms to which humanity has grown accustomed. A global climate model without the moon becomes a model of high variability, a blend of glacial cycles and brief warming periods. It no longer follows stable Milankovitch rhythms, which today are largely shaped by solar and orbital cycles. Without the moon, precession accelerates. Axial tilt destabilizes. Climate rhythms lose predictability. Implications for life. There is a hypothesis that the moon's presence made Earth's climate stable enough for complex life to evolve. If the moon disappears late in planetary history, ecosystems already adapted to gentle climatic oscillations face a far harsher reality. Climate changes occur more rapidly. Periods of stability shrink. This reduces the ability of ecosystems to support large multi-level food webs. Species capable of rapid adaptation gain dominance. Massive ecosystems, such as temperate forests, become less stable as they require long-term consistency. Atmosphere and storms. Changes in axial tilt also influence storm trajectories. And atmospheric intensity. During certain seasons, the temperature contrast between polar and equatorial regions intensifies, creating conditions for powerful cyclones capable of moving enormous air masses. In other epochs, the contrast weakens and atmospheric circulation slows. This produces long sequences of years with unusually frequent storms, followed by eras of reduced atmospheric activity. Together, these oscillations create a highly variable climate system. There is no stable distribution of temperature, humidity, or pressure. Everything depends on the current phase of axial oscillation. Night without moonlight. Solar illumination is another key element. The moon reflects a significant fraction of sunlight at night. Without it, nighttime illumination drops by approximately 20 times. This affects the rate at which Earth's surface cools. In some regions, the crust and atmosphere lose heat more rapidly. This can intensify nighttime phenomena, dew formation, fog, near-surface temperature inversions. On its own, this effect seems minor compared to axial changes. But taken together, these factors reshape the planet's thermal balance. Even small shifts in nighttime cooling rates can influence temperature and humidity distribution over long periods of time. Some researchers suggest that in the absence of the moon, variations in Earth's axial tilt could become so pronounced that over geological timescales, the planet's climate enters a switching regime. In one mode, the polar regions are buried beneath ice sheets several kilometers thick, while equatorial zones experience long periods of stable warmth. In another mode, the ice retreats dramatically, and the planet undergoes a sharp rise in average global temperature. These transitions may occur every few tens of thousands or hundreds of thousands of years, reshaping the geography of the biosphere, redistributing ocean currents, and creating unpredictable conditions in which long-term ecosystem stability becomes difficult to maintain. Carbon balance and instability. Increased climate variability also affects the distribution of carbon dioxide. Vegetation and oceans are the primary regulators of atmospheric CO concentration. Under stable climate cycles, they function as a vast biogeochemical buffer. But during periods of abrupt change, this buffering capacity weakens. For example, the large-scale retreat of glaciers exposes vast land surfaces that actively absorb carbon dioxide. During periods of glacial advance, this absorption decreases and atmospheric CO levels may rise. Such oscillations disrupt climate feedback stability and make the system more vulnerable to cascading change. Even the geographical distribution of rainfall begins to depend on the phase of axial tilt. When the tilt is large, regions that today lie in temperate zones may receive extreme rainfall in summer and severe drought in winter. During epochs of smaller axial tilt, many regions experience more evenly distributed precipitation. As a result, deserts, forests, and grasslands migrate. Natural systems lose their familiar boundaries. Periods of desert expansion alternate with eras of forest recovery. Together, these processes create a planet whose climate resembles a complex, pulsating organism rather than a stable system. Oceans without lunar mixing. There is another crucial aspect, the interaction between climate and oceans. As lunar tidal forces disappear, the vertical mixing of upper and deeper ocean layers weakens. This reduces the efficiency of nutrient transport from the depths. Over time, such changes alter marine biology. Phytoplankton, the foundation of oceanic food webs, depends on nitrates and phosphates supplied from deeper waters. If mixing weakens, ocean productivity declines. Fish populations redistribute. Marine animals alter migration routes. Overall oxygen content in seawater may decrease. Marine ecosystems become less productive and therefore more vulnerable to climate fluctuations. Landscapes in motion. Increased climatic chaos is reflected in landscape processes as well. Periods of intense melting produce powerful river floods, reshape channels, and expand deltas. Cold epochs, by contrast, lead to reduced river flow, drying of lakes, and soil degradation. The landscape begins to change faster than ecosystems can adapt. Animal migrations become more widespread. Stable ecosystems may disappear entirely. No sudden catastrophe, but deep transformation. Thus, the disappearance of the moon does not cause an immediate catastrophe. Instead, it triggers a profound restructuring of Earth's climate system. The planet remains habitable, but life develops under conditions of heightened variability. Earth loses the climatic stability that allowed it to maintain relatively gentle conditions for hundreds of millions of years. Everything becomes more mobile. Cycles grow shorter. Ecosystems become less resilient. Climate becomes more chaotic. In such conditions, the planet's future is no longer predetermined. Each new climate cycle emerges from complex interactions between axial tilt, ocean circulation, atmospheric dynamics, and geological processes. Life without its gravitational rhythm. What happens to living organisms when the primary gravitational regulator disappears, the one that shaped tidal rhythms, nighttime illumination, and seasonal stability? This question reaches beyond physics and climatology into the realm of biological evolution. Life on Earth evolved under cycles tied to planetary rotation and the orbit of its satellite. Many adaptations arose precisely because of repetition. The alternation of day and night, lunar phases, tides, seasons, and precessional rhythms. When the satellite disappears, a portion of these natural rhythms vanishes as well. rhythms that served for millions of years as guides for behavior, reproduction, migration, and ecological competition. The transition into this new environment becomes a serious evolutionary challenge, affecting microorganisms, plants, animals, and even human societies. Disrupted biological clocks. One of the earliest changes is the restructuring of biological rhythms. Many species use moonlight as a reference. This dependence appears in nocturnal predators, migratory birds, marine animals, and even certain insects. With the disappearance of the moon, nighttime illumination decreases by roughly 20 times. This alters the behavior of entire groups of organisms. Nocturnal predators that relied on faint reflected light can no longer perceive their environment as they once did. Species that avoided brightly lit nights lose orientation cues for migration, reproduction, and partner selection. Other sensory systems intensify: smell, hearing, bioluminescence. Organisms unable to adapt their sensory mechanisms face population decline. The collapse of tidal ecosystems. Even more significant is the disappearance of tidal cycles. Countless marine species depend on predictable tides. Certain mollusks, fish, worms, and algae are adapted to environments where coastal zones are submerged and exposed twice daily. Lunar tides created a unique habitat, the littoral zone, where competition and selection followed distinct rules. Without the moon, only weak solar tides remain, roughly 2.5 times weaker. Tidal amplitude decreases noticeably. Coastal ecosystems undergo complete transformation. Large sections of the littoral zone vanish. Habitat space shrinks for organisms adapted to periodic drying. Crabs, barnacles, sea anemones, and many algae-dependent species lose their ecological niches. The disappearance of these zones intensifies competition. Food chains reorganize. Species capable of rapid genetic change, behavioral flexibility, and migration gain dominance. Highly specialized organisms become vulnerable. Littoral productivity declines sharply, affecting the entire marine trophic structure. Fish populations decrease. Marine bird numbers fall. Large marine mammals suffer indirectly. Migration without moonlight. The absence of the moon also alters animal migration. Some species rely on lunar light and phases as navigational cues. Sea turtles laying eggs on sandy beaches orient themselves by the brightness of the horizon. Without natural nighttime illumination, hatchlings may lose direction. Birds that navigate at night lose part of their celestial reference system. They shift toward magnetic or solar navigation, placing additional strain on sensory mechanisms. Navigation errors increase. Some populations may decline simply because too many individuals fail to arrive at their destinations. Evolutionary processes, adaptation, mutation, and natural selection require time. With the disappearance of the moon, many species find themselves under conditions of accelerated selection. Reduced climate stability creates new ecological niches. Some species disappear, others emerge. Within a few 100,000 years, the biosphere may acquire entirely new characteristics. The role of organisms capable of surviving across a wide range of climatic conditions increases. Specialized species, dependent on narrow ecological parameters, become less competitive. This creates a general trend toward an increase in generalist species and a decline in specialists. Oceans and evolutionary pressure. There are hypotheses suggesting that the disappearance of the moon could alter evolutionary pathways for marine organisms. Without tidal forces, ocean mixing weakens, reducing the upward transport of nutrients from deeper layers. Phytoplankton, the foundation of the marine trophic pyramid, experiences mineral nutrient deficiency. Its population declines. This decline propagates upward. Zooplankton numbers fall, followed by fish populations. Large fish and marine predators become fewer in number. and smaller in size. The marine biosphere becomes less productive. This drives a global evolutionary shift toward life forms capable of surviving under conditions of low food availability. Plants under darker nights. The influence of the moon's disappearance on vegetation unfolds differently. Plants do not rely on tides, but they are sensitive to light and temperature. As nights grow darker, plants experience changes in daily rhythms, affecting photoperiodism. Some species depend critically on the duration of day and night. They function like biological clocks, using night length as a signal for flowering and reproduction. When nighttime illumination decreases, this signal becomes less reliable. In certain species, hormone synthesis regulating growth and dormancy is disrupted. This may lead to unusual flowering cycles or reduced agricultural yields. Humanity without the moon. Humanity would also feel the consequences of the moon's disappearance. Even with advanced technology, the human organism remains part of the biosphere. The loss of nighttime illumination affects circadian rhythms. Hormones such as melatonin are regulated by nighttime light levels. Darker nights promote increased melatonin production, which may alter sleep patterns, mood, and behavioral responses. The psychological impact of the moon's disappearance is difficult to quantify. The moon has long been part of culture, mythology, and scientific worldview. Its disappearance becomes a symbol of lost stability. For some societies, this may act as a significant stressor. Cultural aftershocks. There are deeper cultural consequences as well. The moon played a role in calendars, religious cycles, and agricultural practices. Although modern societies primarily use solar calendars, the memory of lunar rituals remains embedded in cultural codes. The disappearance of a familiar celestial body may alter humanity's relationship with space itself. It could stimulate scientific curiosity, create a demand for new explanatory models, and even reshape philosophical perspectives on humanity's place in the universe. A faster, harsher evolutionary world. In the long-term perspective, the post-lunar biosphere becomes more dynamic. Living organisms evolve more rapidly. Selection grows harsher. Adaptive mutations become more frequent. Regions with high climatic variability give rise to new ecosystems. Some animal species may develop new sensory capabilities to compensate for the absence of moonlight. In the oceans, species may emerge that efficiently exploit weak solar tides. On land, organisms capable of enduring regular climatic stress become dominant. Stability gives way to dynamics. Predictability gives way to flexibility. Intelligence under pressure. Changes in the evolutionary environment may even lead to the emergence of new forms of intelligence. In unstable conditions, survival favors those who can anticipate change and adapt quickly. Such environments encourage analytical ability, abstract thinking, and long-term planning. In this sense, the disappearance of the moon is not only a threat, but also a factor that may stimulate the evolution of intelligence. Mixing of life zones. The restructuring of the biosphere also affects interactions between species. As climate changes, the ranges of many organisms shift. Some species migrate toward higher latitudes. This leads to competition between migrating and resident species. New hybrid zones emerge. The loss of stable climatic boundaries creates conditions in which biogeographical regions mix. Species distribution maps grow more complex. The likelihood of new ecological strategies increases. The microbial foundation's subtler biological processes also come into play. Microorganisms, especially bacteria and archaea, adapt faster than all others. Changes in temperature, humidity, and ocean chemistry drive shifts in bacterial populations. This alters global material cycles. Regions once dominated by certain bacterial species become occupied by others. Soil composition changes. Organic decomposition rates shift. Photosynthetic intensity is altered. Microbiological restructuring affects the entire biosphere. Over millions of years, not only ecosystems change, but the very structure of the evolutionary tree itself. The disappearance of the moon becomes one of the factors determining which branches of evolution flourish and which fade. The biosphere ceases to resemble the one we know. It acquires traits typical of systems with high variability. Life becomes more plastic, less tied to stable conditions. The planet turns into a dynamic laboratory where environmental change proceeds faster than in previous eras. A living planet, but a different one. The moon's disappearance affects the biosphere as a complex, multi-level phenomenon. It influences everything from molecular processes to global ecosystems. No level remains unchanged: informational, genetic, behavioral, ecological. Reorganization occurs everywhere. Although the loss of the satellite does not cause immediate biosphere collapse, it creates conditions in which the previous balance can no longer exist. Earth remains alive, but it lives differently. In a mode of constant change, new ecological strategies, and rapid evolutionary cycles. Beneath the surface, what happens to the planet's internal processes when an object disappears that, for billions of years, exerted tidal influence on the crust, mantle, and even Earth's rotation? This question extends beyond surface phenomena, such as ocean tides, into deep geophysical processes within the planet. Earth's crust, asthenosphere, and deeper structures experience stretching and compression under lunar gravity. Even though these deformations are small, their regularity makes the effect cumulative. The disappearance of this periodic load changes stress distributions within the lithosphere. As a result, tectonic processes after the moon's disappearance evolve differently than during the era of tidal forcing. Lunar gravity causes tidal flexing of the crust, altering its geometry by several tens of centimeters each day. These oscillations do not destroy the crust, but they impose rhythmic stress that affects faults and plate boundaries. Some researchers suggest that regular tidal deformation acts like a form of mechanical massage, helping maintain tectonic activity. Because the lithosphere consists of plates moving atop the asthenosphere, any external rhythmic force influences plate boundaries. With the moon gone, tidal deformation amplitude decreases and stresses along faults are redistributed differently. One of the consequences would be a change in the frequency of earthquakes. Although earthquakes primarily depend on the accumulation of energy within tectonic regions, tidal forces often act as subtle triggers. When the moon disappears, some of these triggering mechanisms vanish. This does not mean that earthquakes would stop. Instead, their timing becomes less regular. Energy accumulates more evenly and is released less often, but with greater force. Such a scenario alters seismic statistics. In some regions, the number of weak earthquakes may decrease, while the probability of rare but powerful events increases. Deep planetary processes, geophysical processes inside the planet, also begin to change. Because the moon influences Earth's rotation, tidal braking has long been one of the forces slowing the planet's spin. Without the moon, this braking weakens. Rotational energy is preserved more efficiently. This affects the dynamics of the liquid outer core, where rotation plays a key role in generating Earth's magnetic field. The magnetic field arises from the movement of molten iron and nickel within the outer core. If the rotation rate stabilizes, the structure of these internal flows changes. Some models suggest that the disappearance of the moon could affect both the intensity and the stability of the geomagnetic dynamo. A fragile magnetic shield, Earth's magnetic field protects the planet from solar wind and high-energy cosmic particles. Changes in its structure can influence radiation levels, the configuration of radiation belts, and the stability of the magnetosphere. If the moon's disappearance alters Earth's rotation and redistributes internal energy, the magnetic dynamo may become less stable. This increases the likelihood of geomagnetic reversals, events during which the magnetic poles swap places. Such reversals occurred in the past, but under altered rotational conditions, their frequency may change. More frequent reversals create periods when the magnetic field weakens. During these epochs, Earth's surface receives higher levels of energetic particles, affecting biological organisms, climate patterns, and atmospheric chemistry, precession, and the planet's slow breath. The disappearance of the moon also affects precession, the slow movement of Earth's rotational axis. Precession arises from the interaction between Earth's rotation and the gravitational influence of both the Sun and the Moon. Without the Moon, the precessional regime changes. This alters the distribution of solar heat and climate cycles, but it also reaches deeper. Precessional oscillations exert mechanical influence on the mantle, interacting with convection currents of hot material. These currents transport heat outward, supporting the slow movement of tectonic plates. A change in precession alters convection dynamics and thus affects the planet's slow, rhythmic breathing. Slower tectonics, deeper heat. There are hypotheses suggesting that the disappearance of the moon may lead to a slight reduction in tectonic activity. Tidal forces create subtle movements within the lithosphere, and their absence reduces external energy acting on the crust. Over long timescales, this may slow volcanism. Volcanoes are part of Earth's heat release mechanism. Reduced volcanic activity means slower heat loss. The planet retains internal heat longer. This has no immediate surface effect, but over millions of years, it may alter atmospheric chemistry, especially if volcanic gas emissions decline. Plates, oceans, and chemistry, mantle temperature, and asthenospheric behavior directly influence plate motion. With reduced external stress and persistent internal processes, plate movement may become less dynamic. Some models suggest the lithosphere could grow more stable. Decreased subduction and seafloor spreading alter the productivity of mid-ocean ridges. This affects ocean chemistry as the formation of new crust releases minerals and dissolved gases. If magmatic activity declines, less carbon dioxide and hydrogen sulfide enter the oceans. Gradually, the chemical balance of seawater shifts. Changing landscapes. The moon's disappearance also influences planetary relief. Over billions of years, tidal forces help sustain the dynamics of certain crustal regions. Though not dominant, their loss creates a new equilibrium. In coastal areas where tidal deformation was strongest, the crust may undergo subtle restructuring. Land levels and continental slopes shift slowly. Combined with sea level changes, this gradually reshapes coastlines. Rotation, inertia, and internal balance. The moon's mass influences Earth's inertia axis and internal mass distribution. With the moon gone, the Earth-Moon system reorganizes its angular momentum. This may cause temporary rotational oscillations, signs of the planet seeking a new equilibrium. These oscillations affect internal interactions, including exchanges between the liquid outer core and solid inner core. Changes in rotation shift heat flow zones and modify convection patterns. Some simulations show that mantle temperature gradients may change. Certain convection cells strengthen, others weaken, where hot upwellings intensify. Volcanism increases at hotspot regions. Where flows weaken, activity declines. Volcanism becomes redistributed across the planet's surface. Degassing in atmosphere. Another consequence is altered deep degassing. Volcanoes release carbon dioxide, water vapor, and sulfur compounds. These gases influence climate and atmospheric chemistry. If volcanism declines, the atmosphere receives fewer gases from below. This affects global heat balance, stratospheric chemistry, and even cloud formation. subduction, and long quiet ages. Subduction zones are also affected. Without regular tidal compression and stretching, the conditions governing plate descent change. Subduction geometry, depth, and speed may shift. Over geological time, this influences mountain building, earthquake patterns, and volcanic arcs. Some hypothetical scenarios suggest longer periods of geological calm. These epochs feature stable landscapes, reduced tectonic activity, and extended quiet phases. Erosion becomes dominant. Mountains slowly soften. Lowlands expand. Rivers form vast deltas and sedimentary basins. The planet's geography gradually smooths. Or sudden instability. Yet the opposite scenario cannot be excluded. If the moon's disappearance introduces rotational chaos, internal processes may become unpredictable. Stored heat could trigger sudden volcanic intensification. Enhanced degassing follows. Atmospheric chemistry shifts. Rising carbon dioxide strengthens the greenhouse effect, leading to periods of global warming. In such a scenario, tectonic processes become irregular. Some epochs are marked by long periods of calm, others by sudden bursts of activity. The disappearance of the moon also affects Earth's gravitational field. A mass vanishes from the planet's orbit, a mass that was in constant, dynamic interaction with Earth. Although Earth's own mass remains unchanged, one of the elements responsible for redistributing forces within the planet's satellite system is lost. This alters gravitational potentials. These changes influence the movement of water, atmospheric pressure, and the geoid, the imaginary surface that defines mean sea level. As the geoid reshapes, sea level rises in some regions and falls in others, enhancing geological processes associated with erosion or sediment accumulation. All of this makes Earth's geophysical appearance more variable. Even though the moon's disappearance does not cause an instant restructuring of the lithosphere, it creates conditions in which deep internal processes begin to behave differently. The planet enters a new mode of geophysical existence. There is no sudden catastrophe, only a gradual shift of balance. Processes that were once rhythmic become less predictable. Some cycles weaken, some vanish, others intensify. Rotation, orbit, and loss stability. What happens to Earth's rotation and orbital characteristics when a large satellite disappears? A satellite that participated in distributing angular momentum and stabilizing precession? This question is central to understanding how Earth's position within the solar system changes, and which forces begin to dominate its motion after lunar influence fades. The moon is not merely a body orbiting Earth. It is an active component of a complex, mechanical ensemble, linking Earth's orbit, rotation, axial tilt, and interactions with other planets. The loss of this component disrupts the balance of forces and triggers a restructuring of orbital parameters that shape climate, seasonality, and long-term planetary evolution. Angular momentum and the length of day, the gravitational bond between Earth and the moon, forms a system in which angular momentum is transferred from Earth to its satellite. The moon slowly drifted away by several centimeters per year as Earth's rotational energy flowed outward. If the moon disappears, this transfer stops. Earth's rotation no longer slows at its historical rate. As a result, the length of the day stops increasing. The planet settles into a new rotational regime, different from the one that shaped geological history. This regime influences the atmosphere, the oceans, and internal dynamics. Most importantly, it affects large orbital cycles that interact with solar forcing. Orbital eccentricity. One of the most important parameters is orbital eccentricity, how stretched Earth's orbit becomes. Eccentricity varies under the gravitational influence of other planets, especially Jupiter and Saturn. The moon acted as a stabilizing element, reducing the impact of external resonances. Without it, Earth's orbit becomes more sensitive. Eccentricity may fluctuate across a wider range. During periods of high eccentricity, Earth receives more solar energy near perihelion and less near aphelion. This creates long cycles of warming and cooling, complicating the climate system. During low eccentricity phases, the climate becomes more uniform. But such phases may be shorter. Accelerated precession. Another key parameter is precession, the slow wobble of Earth's axis, similar to a spinning top. Precession arises from the interaction between Earth's rotation and the gravity of the Sun and Moon. Without the Moon, precession accelerates. Cycles that once unfolded over long timescales now occur more rapidly. Faster precession alters the seasonal distribution of solar energy. Earth's position along its orbit changes more quickly relative to axial orientation. Seasons lose stable alignment with orbital distance. Climate cycles grow more chaotic. This affects the long-term evolution of both atmosphere and oceans. Axial tilt instability, Earth's axial tilt, also changes. The Moon stabilized this tilt, keeping it within narrow limits. Without the Moon, the tilt becomes far more sensitive to gravitational disturbances from Jupiter and other planets. Theoretical models suggest the tilt could vary from nearly zero to values approaching 40 degrees. At near zero tilt, seasons disappear and high latitudes become harsh. At large tilt, polar regions receive intense sunlight in summer, melting ice rapidly, but plunge into extreme darkness and cold in winter. Such oscillations create long epochs of radical climate transformation. Resonances and orbital stability. The Moon also participates in resonance interactions within the solar system. Resonances occur when orbital periods align in specific ratios, amplifying gravitational effects. If the Moon disappears, Earth exits certain resonant states. Interactions with Jupiter and other massive bodies change. Some resonances strengthen, others weaken. This alters the long-term stability of Earth's orbit. Mass distribution and inertia. The gravitational interaction between Earth and the Moon affects the system's center of mass. After the Moon disappears, the barycenter shifts into Earth's center. This changes Earth's moment of inertia and influences rotation. Temporary rotational oscillations may occur, variations in day length, subtle instabilities in axial orientation. Though these oscillations fade over time, they initially add another layer of climatic variability. Tidal breaking and atmospheric dynamics. The disappearance of tidal forces also alters rotational balance. With tidal breaking gone, Earth may experience a slight increase in rotational speed during early epochs. This effect is subtle, but it influences atmospheric circulation and air-sea interactions. Magnetosphere and solar wind. The Moon also played a minor role in shaping Earth's magnetosphere. Its disappearance changes magnetic field geometry. Some models suggest the interaction area between magnetosphere and solar wind could increase. This affects auroral energy, radiation belts, and the flux of particles entering the upper atmosphere. Distance to the Sun. Finally, the disappearance of the Moon raises questions about Earth's distance from the Sun. While no major shift occurs, resonance changes may cause subtle variations. For billions of years, the Earth-Moon system remained stable. Without the Moon, Earth continues its journey, still alive, still dynamic, but guided by a quieter, more uncertain set of rhythms. The sky grows darker, the cycles grow softer, and the planet learns slowly to move without its ancient companion. If the Moon disappears, Earth enters a new mode of interaction with the other planets. Small shifts in its orbit may occur over very long timescales. They do not threaten the planet's existence, but they are capable of reshaping long-term climate cycles. It is also interesting to consider a scenario in which the disappearance of the Moon leads to the release of a small portion of orbital energy in the form of microthermal processes. These processes arise from the restructuring of rotation and changes in Earth's moment of inertia. Although this effect is subtle, it may influence atmospheric phenomena. If Earth's rotation becomes more stable, equatorial wind zones begin to reorganize. This affects global atmospheric circulation, especially the trade winds, which play a key role in redistributing heat across near-equatorial regions. Small bodies and lost shielding. It is also important to consider the influence of the Moon's disappearance on orbital resonances with small bodies of the solar system. Asteroids, comets, and meteoroid streams interact with Earth not only directly, but also through the Moon's gravity. The Moon acted as an additional shield, intercepting some incoming objects. If the satellite disappears, small bodies that might once have collided with the Moon can instead reach Earth's atmosphere. This increases the number of meteorites reaching the surface. Over long periods of time, this may affect the chemical composition of both the atmosphere and the surface itself. A more complex orbital era, we can also imagine deeper orbital scenarios. If the Moon's disappearance changes axial tilt, orbital eccentricity, and the speed of precession, Earth enters an era in which its orbit becomes part of a more complex dynamic system. The planet responds more strongly to gravitational disturbances from Jupiter, Saturn, and other planets. Temporary resonant states may form, states that influence climate cycles and axial stability. These temporary configurations can persist for tens of thousands of years, creating epochs of heightened climate variability. Some models even suggest the possibility of weak temporary satellites forming around Earth after the Moon's disappearance. These would be small objects, captured by gravity. They would not replace the Moon, but could create minor tidal effects and influence the paths of certain meteoroids. However, such objects would be unstable and short-lived. They would not significantly affect axial tilt or precession. A new orbital rhythm, long-term orbital changes after the Moon's disappearance define a new dynamic epoch for Earth. Orbital parameters lose the stability they once had. Variations in axial tilt, eccentricity, and precession become more pronounced. This leads to increased climate variability. Earth remains stable in its orbit around the Sun, but it loses the former predictability of its seasons and climate rhythms. Thermal balance without the Moon. What happens to Earth's thermal regime when an object disappears that for billions of years indirectly participated in distributing energy between atmosphere, oceans, and the surface? This question is crucial because climate, tides, nighttime illumination, and rotational parameters are all linked through a shared energy balance. The disappearance of the Moon does not add heat or remove it from the system. Instead, it changes how existing energy is distributed. And it is precisely this redistribution that becomes one of the key drivers of long-term climate change. Darker nights, deeper cooling after the Moon disappears, nighttime illumination drops by roughly 20 times. This leads to faster cooling of soil, vegetation, and ocean surfaces. Although the direct thermal effect seems small, the atmosphere possesses sensitive feedback mechanisms. The rate at which the surface cools affects the structure of the boundary layer, the formation of inversions, and the development of fog. Darker nights increase the temperature contrast between day and night. These contrasts create additional thermal gradients that influence wind speed, flow direction, and the overall structure of the atmosphere. In such conditions, nights may become not only colder, but thermally longer. Without the Moon, the baseline level of nighttime illumination decreases. This affects cloud formation. Some cloud types require a delicate balance between surface cooling and atmospheric moisture. If the surface cools more rapidly, low-level humidity increases, condensing into fog or low clouds. These clouds then trap heat, creating a new balance between cooling and energy retention. Inversions and stagnant air In continental regions, these changes intensify temperature inversions, especially during colder seasons. Inversion layers prevent warm air from rising, creating stagnant zones. Pollutants from natural or human sources become trapped near the surface. This leads to longer periods of smog. Without the moon, such episodes may occur more often as nighttime cooling grows deeper. As a result, stationary high-pressure systems last longer, especially in lowlands and valleys. Atmospheric circulation in a variable world. Changes in atmospheric heat balance affect global circulation. The atmosphere responds to temperature differences between equator and poles. If the moon's disappearance increases the variability of Earth's axial tilt, temperature contrasts become stronger in some epochs and weaker in others. This affects latitudinal wind patterns, the strength of zonal flows, and the distribution of storms. During periods of high axial tilt, seasonality intensifies. The atmosphere responds with stronger thermal gradients, more powerful storms, and intensified frontal systems. During periods of low tilt, the temperature difference between high and low latitudes shrinks. Circulation weakens. The atmosphere becomes sluggish. Storms grow less frequent. The climate appears smoother. But without the moon's stabilizing influence, these epochs, they change more rapidly than they do today. Transitions become sharper, more abrupt. Oceans and lost tidal mixing. The moon's influence on oceanic processes is also essential. Oceans are Earth's main heat reservoir. Lunar tides contribute to ocean mixing. Though this contribution is smaller than wind-driven mixing, it is especially important in deep ocean regions. Tidal waves and currents help mix layers and transport heat downward. If the moon disappears, tidal energy drops almost by half, leaving only solar tides. Reduced tidal mixing stabilizes ocean stratification. Warm surface layers become less connected to cold, deep layers. Heat and nutrients are transported less efficiently. Surface waters heat up faster by day and cool faster by night. Deep waters remain colder and more static. This alters global ocean circulation. In some regions, upwelling weakens, reducing biological productivity. These changes ripple through the entire energy balance of the biosphere. Phytoplankton, the foundation of marine food chains, depends on nutrients rising from the depths. And with weaker mixing, that quiet upward flow begins to fade. If the moon were to disappear, Earth would enter a new mode of interaction with the other planets. Small shifts in its orbit could begin to occur over long periods of time. These changes would not threaten the existence of the planet itself, but they could subtly reshape long-term climate cycles, altering rhythms that have remained familiar for millions of years. It is also fascinating to consider a scenario in which the disappearance of the moon releases a very small portion of orbital energy in the form of microthermal processes. These processes arise from the reorganization of Earth's rotation and changes in its moment of inertia. Although this effect is extremely weak, it may still influence atmospheric behavior in quiet but measurable ways. If Earth's rotation becomes more stable, the equatorial wind zones begin to reorganize. This affects global atmospheric circulation, especially the trade winds that determine how heat is distributed across equatorial regions. The balance of rising and descending air masses slowly adjusts, creating a slightly different breathing pattern for the planet's atmosphere. It is also important to consider how the disappearance of the moon would affect orbital resonances with smaller bodies in the solar system. Asteroids, comets, and meteoroid streams interact with Earth not only directly, but also through the moon's gravitational field. For billions of years, the moon acted as an additional shield, intercepting some objects before they could reach Earth. If the moon vanishes, small bodies that once collided with the lunar surface may instead enter Earth's atmosphere. This would increase the number of meteorites reaching the surface. Over very long timescales, this process could influence the chemical composition of both the atmosphere and the planet's surface. Deeper orbital scenarios can also be imagined. If the disappearance of the moon alters axial tilt, orbital eccentricity, and the rate of precession, Earth enters an era in which its orbit becomes part of a more complex dynamic system. The planet begins to respond more strongly to gravitational disturbances from Jupiter, Saturn, and other massive bodies. This may lead to the formation of temporary resonance states that influence climate cycles and the stability of Earth as rotational axis. Such states can persist for tens of thousands of years, creating extended periods of heightened climatic variability. Some models even suggest the possibility of weak satellite formations around Earth after the moon's disappearance. These could be small objects temporarily captured by Earth's gravity. They would not replace the moon, but they might create minor tidal effects and slightly influence the paths of certain meteoroids. However, unlike the moon, such objects would be unstable and short-lived. They would not have a meaningful effect on axial tilt or precession. The long-term orbital changes that follow the disappearance of the moon define a new, dynamic era for Earth. Orbital parameters become less stable than before. Variations in axial tilt, eccentricity, and precession grow more pronounced. As a result, climate variability increases. The planet remains stable in its orbit around the Sun, but it loses the familiar predictability of seasonal and climatic cycles. What happens to Earth's thermal regime when an object that indirectly participated in energy distribution between the atmosphere, oceans, and surface for billions of years suddenly disappears? This question is essential because climate, tidal processes, nighttime illumination, and rotational parameters are all connected through a shared energy balance. The disappearance of the moon does not add heat or cold to the system. Instead, it redistributes energy that already exists. And it is precisely this redistribution that becomes one of the main drivers of long-term climatic change. After the moon disappears, nighttime illumination decreases by approximately 20 times. This leads to faster cooling of soil surfaces, vegetation, and oceans. Although the difference in thermal influence may seem small, Earth's atmosphere contains sensitive feedback mechanisms. The rate at which the surface cools affects the structure of the near-ground layer, the formation of temperature inversions, and the development of fog. Darker nights intensify temperature contrasts between day and night. These contrasts create additional thermal gradients that influence wind speed, flow direction, and the overall structure of the atmosphere. In conditions of increased darkness, nights become not only colder, but also longer in terms of thermal activity. Without the moon, the level of nighttime background light decreases. This affects cloud formation. Certain types of clouds require a delicate balance between surface cooling and atmospheric moisture. When the surface cools more rapidly, zones of increased humidity form in the lower layers of the atmosphere. These zones may condense into fog or low clouds. In turn, these low clouds trap some heat, creating a new balance between cooling and energy retention. In continental regions, such changes strengthen temperature inversions, especially during colder seasons. Inversion layers prevent warm air from rising, forming stagnant zones. Under such conditions, pollutants released by natural or human processes accumulate near the surface, leading to longer periods of smog. Without the moon, such episodes may occur more frequently as nighttime cooling becomes deeper and more persistent. This increases the duration of stagnant high-pressure systems, particularly in lowlands and valleys. Changes in the atmospheric heat balance affect global circulation. The atmosphere is a vast system that responds to temperature differences between the equator and the poles. If the disappearance of the moon increases the chaotic behavior of Earth's axial tilt, temperature contrasts between regions become more pronounced in some eras and weaker in others. These shifts influence the latitudinal structure of winds, the strength of zonal flows, and the distribution of storms. During periods of large axial tilt, seasonality intensifies, and the atmosphere responds with stronger thermal gradients. This promotes the formation of powerful storms and more intense atmospheric fronts. During periods of small axial tilt, temperature differences between high and low latitudes decrease. Circulation weakens, the atmosphere becomes calmer, storms occur less frequently, and the climate appears more uniform. However, without the stabilizing influence of the moon, these epochs faster than today. The atmosphere transitions between active and passive modes more often, and the boundaries between them become sharper and more abrupt. The moon also plays an important role in oceanic processes. The oceans are Earth's primary heat reservoir. Lunar tidal forces contribute to ocean mixing. Although this contribution is small compared to wind-driven mixing, it is particularly significant in deep water regions. Tidal waves and currents create dynamics that promote layer mixing and the transport of heat into deeper layers. If the moon disappears, tidal energy is reduced almost by half, leaving only solar tides. The reduction in tidal mixing stabilizes ocean stratification. Warm surface layers become less connected to cold, deep layers, reducing the efficiency of heat and nutrient transport. As a result, the upper ocean warms more quickly during the day and cools more rapidly at night, while deep layers remain cold and less dynamic. This affects ocean circulation as a whole. In some regions, upwelling of deep waters weakens, reducing biological productivity. Such changes influence the entire energy balance of the biosphere, since phytoplankton, the foundation of marine food chains, depends on the supply of nutrients from depth. It is also possible to consider the influence of the moon's disappearance on Antarctic circulation. The Antarctic circumpolar current is one of the largest and most powerful ocean currents on Earth. If the geomagnetic field becomes less stable, the flux of charged particles reaching the stratosphere increases. This leads to temporary periods of ozone layer weakening. During such periods, ultraviolet radiation at the surface becomes stronger. Although this effect is not catastrophic, it influences the biosphere, especially phytoplankton and plants that are sensitive to ultraviolet light. Changes in cloud cover become one of the key consequences of the moon's disappearance. Clouds play a vital role in Earth's thermal balance. This strengthens the formation of low clouds in some regions, while reducing their presence in others. Because the surface cools faster than the surrounding air, dense fog layers develop, especially in regions with high humidity. These layers trap heat, hold pollutants near the surface, and create long periods of reduced visibility. The structure of cloud cover depends closely on atmospheric dynamics, and in a more chaotic climate, cloud systems become less stable. In some periods, the amount of high-level clouds increases. In other periods, low clouds dominate, enhancing surface cooling. These oscillations widen the gap between daytime and nighttime temperatures. In the absence of the moon, such contrasts become more pronounced because the gentle lunar light that once soft nighttime cooling is no longer present. The disappearance of the moon also affects atmospheric optics. Moonlight once created subtle optical phenomena, lunar rainbows, halos, faint coronas. Without this light, the night sky becomes much darker. This reduces the number of photochemical reactions occurring in the upper atmosphere at night. This slows chemical processes responsible for cleansing the atmosphere of pollutants. The hydroxyl radical plays a crucial role in breaking down methane, tropospheric ozone, and other contaminants. When its concentration declines, these substances remain in the atmosphere for longer periods. The chemical composition of the atmosphere also changes due to intensified nighttime cooling. A colder surface promotes condensation of moisture, but it also reduces evaporation rates. When evaporation decreases, the distribution of water vapor shifts. Water vapor is the most important greenhouse gas, and its concentration directly influences temperature. Under altered atmospheric dynamics, water vapor concentrations vary depending on axial tilt cycles. During periods of large axial tilt, atmospheric water vapor increases due to intense summer warming. During periods of small axial tilt, water vapor concentrations decline, weakening the greenhouse effect. The disappearance of the moon also affects chemical cycles related to carbon dioxide. The oceans are the primary regulators of atmospheric CO. They absorb carbon dioxide and release it back into the air. With reduced tidal mixing, the ocean becomes less effective at absorbing gas. Upper layers saturated with carbon dioxide become separated from deeper layers that once served as reservoirs. During warming periods, this increase becomes even stronger because warm water holds less dissolved gas. This creates a positive feedback loop. Rising temperatures increase carbon dioxide levels, which in turn intensify warming. Under conditions of strong climatic variability, plant communities struggle to maintain stability. During warming periods, vegetation expands and absorbs more carbon dioxide. During cooling periods, vegetation retreats, reducing absorption. These fluctuations alter atmospheric chemistry. Without the moon, vegetation responds more quickly, but also less predictably. We can also consider the influence of the moon as disappearance on chemical processes occurring above the oceans. If ocean circulation becomes less active, the production of marine aerosols decreases. These aerosols act as cloud condensation nuclei. When their numbers decline, cloud cover diminishes. This allows more solar energy to reach the surface, creating a warming effect. However, during periods of strong winds, aerosol production increases and cloud cover grows. This enhances the reflection of sunlight and produces a cooling effect. Without the moon, such oscillations become more pronounced as the system operates in a state of variable stability. Atmospheric chemistry is also influenced by the amount of dust transported by winds. Under strong climatic fluctuations, desert regions may expand, increasing dust production. Dust affects cloud formation, enhances absorption and scattering of solar radiation, and alters the chemical composition of the upper atmosphere. During periods of powerful winds, dust can be lifted into the stratosphere, changing the optical properties of the atmosphere. During calmer periods, dust settles, altering the rates of chemical reactions near the surface. The disappearance of the moon also affects atmospheric electricity. The moon influenced Earth's electric field through interactions with the ionosphere. Its absence alters the structure of this field. This affects thunderstorm activity, lightning frequency, and ionization processes. During periods of intensified solar wind, lightning activity may increase. This influences the production of nitrogen oxides, which are important components of atmospheric chemistry. All of these processes together form a new gaseous dynamics of the atmosphere. It becomes less stable and more sensitive to changes in climate, ocean circulation, and solar activity. No single mechanism dominates its behavior. Instead, a network of interconnected chemical and physical processes operates in a state of heightened sensitivity to even the smallest changes. What happens to a planetary system when an object disappears? An object that played a key role in distributing angular momentum, attracting meteoroids, softening the impact of the cosmic environment, and maintaining rotational stability? This question extends beyond Earth's immediate surroundings and reaches into the energetic interaction between the planet and the space around it. The moon acted as a filter. It reduced the amount of cosmic debris, reflected part of the sunlight, created gravitational resonance patterns, and participated in redistributing solar energy. The loss of such an object reshapes the entire structure of Earth's external interaction with space. One of the most significant consequences is a change in meteoroid flux. The moon served as a natural shield for Earth. Its gravitational field deflected or captured many small bodies. A large portion of meteoroids traveling through near-Earth space collided with the moon rather than Earth. With the disappearance of the moon, Earth becomes exposed to a greater number of micro-impacts. These collisions rarely threaten life at the surface. but they affect the upper atmosphere, causing localized ionization, plasma trails, and changes in the structure of the thermosphere. Over thousands of years, this process alters the distribution of elements in the upper atmosphere. An increased number of meteoroids also affects chemical processes. Under enhanced flux conditions, the composition of atmospheric aerosols gradually changes. This influences cloud formation, planetary albedo, and chemical reactions in the stratosphere, especially reactions related to ozone. Certain elements, such as iron and magnesium, participate in catalytic processes that destroy ozone. At times, this can weaken the ozone layer, particularly during periods of high meteoroid activity. The disappearance of the moon can also be considered in relation to the distribution of cosmic radiation. The moon acted as a secondary reflector and absorber of high-energy particles. Its surface reflected part of the cosmic radiation and absorbed another part. Without it, a larger volume of space interacts directly with Earth. This changes the distribution of particle fluxes penetrating the atmosphere. During periods of increased solar activity, the of protons and electrons can grow. In the absence of the moon, Earth's magnetosphere receives a greater number of high-energy particles, which can trigger additional ionization processes and changes in atmospheric density. The structure of the radiation belts is altered. Earth's radiation belts form through the interaction of charged particles with the magnetic field. The moon exerted a weak gravitational influence on this system. Without it, the structure of the belts changes. Some models suggest that the disappearance of the moon may allow charged particles to penetrate deeper into the atmosphere. This makes the atmosphere more sensitive to cosmic storms and solar flares. During periods of weakened magnetic field strength, the likelihood of particles reaching lower atmospheric layers increases. The disappearance of the moon can also be considered in relation to Earth's thermal radiation. The moon reflected a small fraction of sunlight, providing faint nighttime illumination. Without it, the night side of the planet becomes almost completely dark. This accelerates heat loss. Such energy exchange affects surface temperature. Faster cooling creates stronger temperature contrasts, which influence atmospheric dynamics. The moon's role in stabilizing Earth as axis of rotation affects how the planet interacts with solar radiation. When axial tilt fluctuates, the distribution of solar energy across latitudes changes. This alters the overall thermal balance. With a large axial tilt, polar regions receive more solar energy in summer and much less in winter. This produces cycles of melting and freezing, leading to long-term changes in albedo. One can also consider the influence of the moon's disappearance on the geometric parameters of Earth's interaction with the solar wind. Earth's magnetic field interacts with the solar wind, forming the magnetosphere. Within it exists the magnetotail, whose shape depends on planetary rotation and the orientation of the magnetic field relative to the Sun. The moon interacted with this tail, creating small disturbances. Without the moon, the shape of the magnetotail becomes more dependent on solar conditions. During strong solar storms, the magnetosphere may compress more strongly than it did when the moon was present. This affects atmospheric density in the upper layers. In addition, the disappearance of the moon alters gravitational interactions between Earth and other bodies. Earth enters a system of interactions in which the moon was once a component. When this component disappears, Earth becomes more sensitive to resonances with Jupiter. These resonances can affect Earth's orbit, producing small but significant oscillations in eccentricity and orbital tilt. Such oscillations influence climatic cycles, the length of seasons, and the distribution of solar energy. The disappearance of the moon can also be considered in relation to the thermal state of Earth's interior. Earth's rotation and its interaction with the moon created tidal friction. This friction was partially converted into heat within the planet. Without the moon, this source of heat disappears. Because internal heat escapes into space very slowly, the loss of this additional source leads to a gradual reduction in heat flow over millions of years. This may alter mantle convection and the structure of tectonic processes. The question of how efficiently Earth interacts with solar energy becomes especially important in the absence of the Moon. Temperature cycles become more diverse. During periods of strong axial tilt, seasonal contrasts intensify. The distribution of solar energy across the surface becomes less stable. Under such conditions, the atmospheric heat balance becomes less steady. Some regions become significantly hotter in summer and much colder in winter. These extremes affect ice cover, the structure of ocean currents, and overall climate dynamics. The disappearance of the Moon can also influence atmospheric pressure. Pressure depends on surface temperature and the distribution of air mass. With stronger temperature contrasts, pressure becomes more unstable. Long-lasting high-pressure systems form, alternating with periods of low pressure. These oscillations affect air circulation. Without the Moon, these cycles become more irregular. The Moon's role in forming atmospheric tides disappears, altering pressure dynamics in tropical regions. These tides once contributed to the formation of certain circulation zones, such as descending air motions linked to heat distribution. Without this influence, the atmosphere becomes more sensitive to solar heating. Solar tides become the only remaining rhythmic driver in the atmosphere. One can also consider the influence of the Moon's disappearance on Earth's interaction with the interplanetary environment. The Moon created a region of gravitational influence that altered the trajectories of certain charged particle streams. Without it, these streams are redistributed differently. This changes the structure of interplanetary dust in near-Earth space. Without the Moon, some particles that previously settled on its surface may cross near-Earth orbits and enter Earth's atmosphere. This changes the quantity of charged and particulate matter entering the atmosphere. The disappearance of the Moon can also affect plasma processes. Plasma within the magnetosphere is sensitive to electric and magnetic fields. If the loss of the Moon alters Earth's rotation rate, this influences the magnetic dynamo and field structure. Under such conditions, the magnetosphere becomes more dynamic. During strong solar storms, the magnetic field may compress to levels at which enhanced radiation reaches the upper atmosphere. This affects ionization, the formation rate of molecular ions, and the balance of chemical reactions. Earth's night side becomes fundamentally different. Without the Moon, the night sky becomes much darker. This affects nighttime thermal radiation levels. A darker sky allows energy to escape more rapidly. Cooling zones form and may expand. Under these conditions, temperature inversions become more frequent. Inversions influence the distribution of pollutants and the structure of the lower atmosphere. Finally, one can consider the influence of the Moon's disappearance on long-term climate cycles. Because the Moon stabilized Earth's axial tilt, many climate cycles depended on its presence. Without it, precession accelerates. This means climatic changes occur more rapidly. For example, the Milankovitch cycle associated with precession may become shorter. This alters the seasonal distribution of solar energy. New climate regimes emerge, in which glacial and interglacial periods may replace one another more quickly. Earth's interaction with cosmic processes becomes more dynamic and less predictable. There is no longer a stabilizer that keeps Earth's axis of rotation within a narrow range. There is no object that partially reflects sunlight and creates a gentle glow at night. There is no natural shield that intercepts part of the cosmic debris. Because of this, Earth enters an era in which its energetic and dynamic connections with space become more intense. One can consider the influence of the Moon's disappearance on atmospheric dynamics in polar regions. Auroras become more frequent and more intense. This is linked to the increased penetration of solar particles. During such periods, the chemical composition of the upper atmosphere changes. The concentration of nitrogen compounds increases, and some of them descend into lower atmospheric layers, influencing chemical reactions. Earth becomes more exposed to long-term cycles of solar activity. During periods of weak solar wind, the atmosphere receives less energy and the magnetosphere compresses less. During periods of strong solar wind, the atmosphere is subjected to greater fluxes of charged particles. In such times, the temperature of the thermosphere can rise and air density can change. This affects the orbital decay rate of artificial satellites and alters the structure of space debris in near-Earth space. Thus, the disappearance of the Moon changes the dynamics of Earth's interaction with space. The planet remains part of the solar system, but the parameters of its connection with the cosmic environment become different. Some processes intensify, some fade away, and others acquire entirely new characteristics. What happens to the geography of the planet, to the distribution of biomes and landscape structures, if the object that helped maintain relative climatic stability for billions of years disappears? This question reveals not only climatic or biological changes, but large-scale reorganizations of natural zones, water systems, vegetation, ice sheets, deserts, forests, and coastal regions. Geography is a dynamic system dependent on climate, tectonics, and the hydrological balance. When the Moon disappears, part of the binding mechanism that kept this system relatively stable also disappears. Natural zones depend on the distribution of heat, moisture, solar radiation, and seasonality. All of these parameters change after the Moon is gone. Variations in axial tilt become significantly stronger, meaning that climate can reorganize more rapidly than it does today. Geography responds by forming new vegetation zones, shifting forests, expanding deserts, and reshaping ice sheets. One of the first major transformations occurs in the polar regions. Polar ice caps depend on temperature and the amount of solar energy they receive. During periods of large axial tilt, polar summers become warmer, leading to intense ice melting. Ice sheets shrink and in some epochs retreat hundreds of kilometers. This causes sea levels to rise. During periods of small axial tilt, polar regions receive less solar energy even in summer. Under such conditions, ice expands. Ice sheets spread into mid-latitudes, covering vast territories. The geographical map of the planet begins to change according to the phase of axial tilt. The expansion and retreat of ice sheets reshape the landscape. During expansion phases, glaciers erode surfaces, transport material, and carve landforms. During retreat phases, glaciers leave behind vast sediment-filled plains. These processes occur faster than in the modern era because axial tilt fluctuations are stronger. Glacial cycles become shorter but more intense. Landscape evolution accelerates. The disappearance of the Moon also affects the distribution of deserts. Deserts depend on atmospheric circulation, which is controlled by temperature gradients. During periods of large axial tilt, stronger seasonal contrasts lead to the expansion of desert zones. In such times, large parts of subtropical regions experience prolonged droughts. Deserts may expand northward and southward, occupying areas that today are grasslands or forests. During periods of small axial tilt, atmospheric circulation becomes more uniform. Some deserts may shrink. Regions emerge where precipitation is distributed more evenly over long epochs. Vegetation begins to advance into former desert areas, creating temporary phases of ecosystem recovery. However, these phases are short-lived as the geographic system becomes more variable. The disappearance of the Moon also influences boreal and temperate forests. These forests depend on temperature, precipitation, and the duration of cold seasons. With strong axial tilt fluctuations, climates in temperate latitudes become less predictable. During periods of large tilt, long warm summers accelerate forest growth. But these phases alternate with harsh winters that can lead to mass plant die-offs. Forest ecosystems are constantly reorganized. In some epochs, forests advance northward. In others, they retreat. Boreal forests experience especially strong changes. During periods of small axial tilt, forest growth slows as summers become cooler and winters longer, increasing snow cover. Under prolonged cooling phases, boreal forests contract. Tropical regions are also affected. The tropics rely on stable solar heating and regular rainfall. Monsoon systems and tropical precipitation are sensitive to heat distribution between land and ocean. With increased climatic variability, monsoons become less predictable. In some epochs, they intensify, bringing heavy rains that support dense tropical forests. In others, they weaken, leading to drying in regions that are currently forested. Tropical ecosystems become more fragmented, forming mosaics of alternating wet and dry zones. The structure of rivers and lakes also changes. As climate shifts, precipitation patterns, snow and ice melt rates, and seasonality are altered. During periods of strong axial tilt, rivers carry more water in summer, but experience lower levels in winter, leading to stronger seasonal fluctuations. During periods of small tilt, seasonality is smoother, and river levels become more stable. Lakes follow similar cycles, expanding during warmer periods and shrinking during cooler ones. These processes reshape the geographic distribution of freshwater resources. Coastal regions undergo major transformations as well. Sea level depends on water temperature and the volume of ice sheets. During periods of strong axial tilt, sea levels rise as glaciers melt. Coastal regions flood, new bays form, and existing shorelines disappear. During periods of small axial tilt, sea levels fall. Large sections of continental shelves become land. New plains emerge, suitable for life. Geography changes again. The disappearance of the moon also influences volcanism and mountain building. Although the moon's direct influence on tectonics is limited, its absence affects plate dynamics. In some regions, volcanic activity may decrease, reducing the formation of new mountain ranges. Under such conditions, erosion becomes the dominant process. Mountains erode faster than they form, leading to a smoother relief. Hydrological cycles become more dynamic. During periods of intense warming, evaporation increases, strengthening rainfall systems in some regions while creating droughts in others. Axial tilt fluctuations lead to uneven precipitation distribution across the planet. All of this directly affects water resources, agriculture, and ecosystems. The disappearance of the moon also influences soil salinization. In regions where precipitation becomes less regular, evaporation intensifies. This leads to the accumulation of salts in the upper soil layers. During cooling phases, droughts may alternate with episodes of heavy rainfall, washing salts deeper into the ground. As a result, the geographical map of saline soils becomes dynamic, constantly shifting over time. Biomes respond to climate change, not only by moving across the planet, but also by altering their internal structure. During warming periods, forests in northern latitudes expand their range. Yet after a few thousand years, the climate may cool again and forests retreat. Such variability reduces ecosystem stability. In these conditions, species extinctions occur more frequently, while the emergence of new species accelerates. This reshapes the planet's biogeographical boundaries. The disappearance of the moon also affects soil formation processes. Soils develop under the combined influence of climate, vegetation, and hydrology. In a more variable climate, soil formation accelerates during some epochs and slows during others. During intense warming phases, humus forms more rapidly, but these periods are followed by epochs of erosion that strip away the fertile topsoil. Soil cycles become faster than they are today. Earth's geography turns into a highly dynamic system, where changes occur more rapidly and more intensely than during the era when the moon was present. There are no stable natural zones, no fixed boundaries for deserts, forests, steppes, or tundra. Everything shifts, expands, and contracts depending on axial tilt, solar energy distribution, and the internal dynamics of the atmosphere and oceans. But what happens to the human mind? What happens to psychological well-being, cultural structures, scientific theories, technological development, and the long-term trajectory of civilization if the object that served as a source of time, orientation, stability, and reflected cosmic light throughout all of human history suddenly disappears? This question reaches far beyond biology and physics. It touches social, philosophical, scientific, and emotional dimensions of human existence. The moon has always been part of collective consciousness. It shaped cultural symbols, ancient astronomy, medicine, religion, art, agriculture, and even fundamental worldviews. Its disappearance alters psycho-emotional balance, social structures, and the direction of scientific progress. The psychological impact is among the first profound changes. For humans, the night sky has always been a framework for time perception. The moon provided soft illumination, allowing shapes and movement to be perceived even in darkness. Without it, the night sky becomes darker than at any other time in human history. This depth of darkness affects emotional states. Humanity evolved in an environment where moonlight was part of the natural world. Its absence creates a sense of emptiness. For some people, nighttime becomes harder to navigate emotionally, as the subjective feeling of safety decreases. The disappearance of the moon also influences human biological rhythms. Circadian cycles are regulated not only by sunlight, but also by lunar illumination. Nighttime brightness affects hormonal processes. In complete darkness, melatonin production increases. This alters sleep patterns, mood, and activity levels. Some individuals may experience prolonged drowsiness, while others develop disrupted sleep cycles. The human brain is adapted to changing light levels, and altering these cycles affects behavior, cognition, and emotional stability. Instinctive fears and ancient responses also resurface. Darkness activates deep evolutionary mechanisms of anxiety. In a world without a natural satellite, societies may experience rising levels of unease. In cultures where lunar rituals held significant meaning, the moon's disappearance may trigger collective psychological crises. Social structures undergo change as well. The moon played a role in calendars. Many ancient calendars were based on lunar cycles, guiding agricultural seasons, religious ceremonies, and daily rhythms of life. Even though modern societies rely on solar calendars, the memory of lunar time persists. Without the moon, a visual anchor that shaped traditions vanishes. Some cultures may attempt to reconstruct symbolic systems, searching for new reference points. Agriculture is indirectly affected. While modern farming depends heavily on technology, traditional practices based on lunar phases are re-examined. Practitioners of organic agriculture may abandon certain rhythms. Without the moon, nighttime temperatures drop, affecting plant growth. This alters agricultural cycles. Art transforms as well. The moon has been one of the central symbols of global culture. Its disappearance gives rise to new artistic movements. People begin to perceive the night sky differently. Without a bright satellite, the sky darkens, revealing the Milky Way in greater detail. This inspires new poetic and visual imagery. Artistic expression may shift toward darker, more philosophical themes. Science gains a powerful new impulse. The disappearance of the moon is an event that demands explanation. Humanity intensifies its study of space. Astronomy gains priority. Scientific institutions focused on cosmology, celestial mechanics, and planetary science face entirely new challenges. The loss of a massive object forces a revision of gravitational models. Scientists search for causes, constructing new theories. Human space programs also change. The moon was the nearest target for exploration, a testing ground for technology and a foundation for future bases. Without it, space exploration follows different paths. Attention shifts toward Mars, asteroids, and nearby planets. Deprived of a natural satellite, humanity begins to imagine artificial ones. Projects emerge to create orbital structures capable of serving as artificial moons. Energy technologies evolve as well. Some concepts, such as lunar reflectors or moon-based power stations, lose relevance, while new ideas appear. Orbital mirrors designed to regulate Earth's illumination may be developed as an attempt to compensate for the loss of nocturnal light. Philosophy undergoes transformation. The moon symbolized permanence. Its disappearance confronts humanity with the fragility and impermanence of the cosmos. People begin to rethink their place in the universe. In some cultures, new myths arise, stories explaining why the moon vanished, forming new symbolic frameworks. Human migration patterns may also be affected. As geography and climate change, some regions become less suitable for life. Large populations move toward more stable environments. New settlement forms emerge, adapted to shifting conditions. And finally, the disappearance of the moon influences global security itself. As cosmic danger increases, especially the threat posed by meteorites, governments begin to develop new systems of planetary protection. Orbital interception platforms appear, along with advanced radar networks and detection technologies capable of tracking objects long before they approach Earth. This leads to accelerated development in aerospace engineering, space defense systems, and global monitoring infrastructures. The disappearance of the moon also reshapes educational systems. Astronomy, once considered a niche discipline, becomes critically important. People begin studying celestial mechanics more deeply, seeking to understand not only how the moon vanished, but how similar cosmic events might occur in the future. New scientific fields emerge, dedicated to the analysis of large-scale cosmic phenomena and planetary stability. Religions are affected as well. The moon was deeply embedded in mythologies across civilizations. Its disappearance forces reinterpretations of sacred texts. In some traditions, new rituals appear. People search for new spiritual reference points, attempting to restore meaning in a sky that has fundamentally changed. The perception of time itself transforms. The lunar calendar ceases to exist as a natural system. Humanity relies solely on solar cycles. This alters cultural rhythms, social traditions, and the psychological sense of temporal flow. Architecture evolves under darker nights. Cities require new forms of illumination. Architects design advanced lighting systems that account for deeper, longer darkness. Urban concepts change. Cities glow differently, carefully balancing safety, energy efficiency, and psychological comfort. Human health and biology are also influenced. Changes in light exposure affect circadian rhythms, microbiota balance, immune responses, and hormonal regulation. Mental health becomes more sensitive to seasonal variations. In some regions, seasonal depression becomes more common. People search for technological and environmental solutions to compensate for the loss of natural night light. At the same time, astronomy enters a new golden age. The night sky becomes significantly darker. Without lunar glare, distant galaxies, nebulae, and faint cosmic structures become easier to observe. The disappearance of the moon is not only a loss, but also an unexpected window into the deeper universe. Artificial lighting intensifies. Dark nights push humanity to illuminate the world more aggressively. This affects nocturnal ecosystems. Animals that evolved under soft moonlight now face strong artificial illumination, altering migration patterns, feeding behavior, and biological cycles. Mass culture responds quickly. Films, books, music, and games emerge, all centered around the vanished moon. The event becomes a symbol of a new era, an age of uncertainty, adaptation, and cosmic awareness. Global politics shift. Changes in geography and climate intensify competition for resources. New zones of conflict appear, but also new opportunities for cooperation. International structures evolve, adapting to a world without its ancient celestial companion. Human dependence on technology deepens. Darkness strengthens the reliance on artificial systems that regulate light, temperature, and environmental comfort. Entire infrastructures are built to reduce stress and stabilize human psychology. Space navigation also changes. Many spacecraft once relied on the moon for gravitational maneuvers. Without it, interplanetary trajectories must be redesigned. Deep space exploration adapts, finding new paths through the solar system. And yet, despite all difficulties, humanity adapts. Psychology, culture, science, and technology slowly discover new ways to perceive reality without the moon. This process becomes part of civilization's evolution, slow, complex, layered, and deeply human. And as you listen to this thought, let it fade gently into the background, like a distant cosmic echo, reminding you that even in a changing universe, adaptation is quiet, inevitable, and calm. You can rest now. The universe continues its motion, slowly, silently, while you drift into sleep.